Well, good morning, grade 11s. I'm actually recording this on Sunday night because I have a very busy day tomorrow, so I want to get this posted before I go to bed. All right, so here's the deal. So far, we have been looking at magnetism. Okay, so this is sort of the second half. We looked at electricity first and electric circuits. I still haven't gotten around to marking that quiz. I will get to it, but yeah, everything in good time. So now we're going to look at the connection. We talked about electricity, then we talked about magnetism. Now we're going to look at the connection between those two things. Okay, and we're going to start with this, number one. This was discovered probably by accident, actually. Someone in a lab noticed that what they did was they had a circuit on, like sort of picture my classroom. Okay, you have like a circuit on one side of the table, okay, like on one table on one side of the classroom, and then your battery, which they had invented in the 1800s, right, in the late 1800s. Your battery is on the other side, on another table, okay, and there's wires that are running across in between, and those wires are just hanging down side by side. If you were to turn on that power supply, if there's enough current, what you would find is those two wires will attract each other from, like, the reason why they attract each other when there's current flowing is because for some reason, while there's current flowing, that copper wire, which is not a ferromagnetic element, will produce a magnetic field. Okay. Now this is electromagnetism. It's electricity producing magnetism. Okay, and yeah, it's kind of cool. It's actually what causes magnetism, just generally speaking. Okay, we never really talked about why certain elements are magnetic. Well, it has to do with the spinning charges that, like the electrons have spin, and for some elements, most elements, the spins cancel out and you get no net magnetic effect. Okay, but for the ferromagnetic elements, they don't have spins that completely cancel out, and so each atom becomes magnetic. So it's kind of cool. Here's the key point. Okay, so the key point here is that moving charges create magnetic fields. And really, that's where magnetic fields come from in the first place. Okay, so moving charges create magnetic fields. Now what I've done here, and hopefully this will work, is I've got a little animation. What does a magnetic field look like around a wire? Okay, like let's say a wire is carrying electricity. Well, if it's carrying electricity, if you plug in like a power source and turn it on, you're going to find that if you place a compass needle next to the wire, it'll dip when the electricity is flowing through the wire. So here's how that works. Okay, I'm gonna load this. Okay, so it's going to take a moment. If it works at all. Okay, here we go. The internet's a little slow these days. All right, so here's the deal. Here we have a battery, and the battery is producing electricity, and conventional current flows out of the positive terminal and then around the circuit and then into the negative terminal. So there are the electrons going around. Now take a look, okay, at the weird little circles that are sort of spinning around the wire. That represents the magnetic field, okay, on that sort of piece of paper that's surrounding the wire. That represents the magnetic field lines, okay? Now, what we'd find is that these lines would form a clockwise orientation, pardon me, around the wire, okay, like this. And that's what they're trying to show you there. Now, they've animated it, but really it wouldn't be animated. So look, let me show you. Let's say you have current, okay, that is flowing. I've got this current flowing the other way. Doesn't really matter, okay? I've got it flowing up instead of down through the paper. And what you would find is these compass needles, okay, these are compasses, okay, all of these things, they would orient themselves like this. Now remember, a compass has a little north end and a south end on it, right? This is the north end and the south end. The arrows are always the north end. So it would form, in this case, a counterclockwise circle around the wire. Okay, now here's our current. That is the current. And the current here is flowing upwards. Okay, so here we see it going up like this. That's what the arrow represents. So there's our current coming up through the wire like that. Okay, and that is a copper wire. So when you have a straight conductor, what happens is you always get a circular magnetic field that will form around the wire when it's carrying current. Now, if the current is flowing downwards, okay, you would get a clockwise orientation around the field. If it's going upwards, like you see here in this image, it would be counterclockwise. Okay, so here we see it here. Okay, and this right-hand rule, that's your right hand. Okay, this is a little trick to help you remember which way the field is oriented around a straight wire. So if I take my thumb and point it upwards along with the current, so here that points to the current flowing up, then my fingers of my right hand will wrap in a counterclockwise, okay, direction around the wire, and that's the field is counterclockwise, right? So this is the right hand rule. Now, if we were going to have an exam, which we won't, but on a test, normally I would have students, because this is open book, it makes it kind of pointless, but I'm going to ask anyway. They're easy questions. I would show you a picture of a wire like this, and you would have to tell me what the direction of the field is, clockwise or counterclockwise. Okay. Now, in the example with the animation, we see that this is actually clockwise. Okay, so that's if the current's flowing down. I can't really draw on that one, so if it's flowing down, we end up with a clockwise field, but if it's flowing up, then the field reverses and it becomes counterclockwise. So you can tell what direction the current is flowing, and you can tell by which direction the magnetic field is in. Okay, so if it's clockwise, the current is flowing up. It's counterclockwise, it's flowing down. Sometimes we look at the cross section of the wire. Now what that means is a cross section of a wire is if like we were to cut the wire. Okay, let's say you take this wire and cut it, but then you look down at it. Okay, if you were to look down at a section of wire, it would look like a circle. So a wire is just a cylinder, and if you look at its cross section, it looks like a circle. Okay, so let's say that's your wire. Okay, now it's not a circle of wire, like it's like a piece of wire that is pointing at you. Okay, and the wire, like picture a wire like like a straw. Okay, like this guy's right hand is holding kind of like a straw. Okay, except it's not hollow, it's solid metal, right, inside. Okay, there's a copper wire in there, but you're looking down through the straw. That's what I mean, by remember it's Sunday night for me. That's what I mean by cross-sectional view. Okay, so that's the cross-section of the wire. And the way we draw current in this scenario, I'm going to use the color blue. If I put a dot, okay, the dot means the current is toward you. Okay. Now, if I draw another cross-section of a wire, and again I'll draw this time the current represented by an X, this means away from you. Okay? So the current is away. Okay? Like into the page of the book or the laptop screen or whatever. Okay? Out of the page. In other words, this little dot here, the dot represents like a ball coming at you. The X represents a ball going away from you. So into the wire and out of the wire. Now I'm going to use red to indicate the magnetic field. If I take my right hand and I wrap it around this wire with a dot in it, my thumb pointing towards me, sort of picture like like you're going to suck on your thumb or something, right? It's pointing towards your face because that dot is coming towards me. Then my fingers will wrap around. That's not what I wanted. I wanted red. My fingers will wrap around the wire in a counterclockwise direction. So that represents the field. Okay, and this is often how the textbook draws them. Okay, now if I take my thumb and stick it into the laptop screen according to the X here, well then my fingers will wrap around the wire, but this time in the clockwise direction. Okay, so that represents the magnetic field. Sometimes we use the letter B to represent a magnetic field. Okay, as a variable, I for current, right? V for voltage, B means magnetic field. Anyway, wires carrying electricity produce magnetic fields. The cool thing about this, okay, is even though copper, which the wire is made of, is not a ferromagnetic element, it's the current, not the copper, that's creating the magnetic field. Like even if you shot an electron through the air, okay, it would create a magnetic field as it travels through the air. All moving charges do. Okay, so there you go. That is how it works for a straight wire. Now, the story doesn't end there. Okay, what if we take the wire? Now, if you're an engineer, okay, here's how it works for a straight wire. But what if you were to take a wire and then curl it up into a coil? Okay. Now, if you do that, let's give it a moment. Okay. Here's your coil, and your coil produces a magnetic field that actually looks exactly like a bar magnetic field. So this is called, here, let's divide it like this. A straight wire. B, this is a coil, or your book calls it a solenoid. It's a weird word, but anyway. Oh no, what am I doing? That's still a straight wire. Pardon me. Sunday night, guys. Okay, B, a coil, or solenoid. Okay, again, you pass this, you attach this coil of wire to a battery, current will be forced to flow in the wire, and like all these loops of wire behave very much like a bar magnet. Okay, now I think I show a picture of it here somewhere. No, I didn't show it. All right, just let me show you how that works. So if I were to draw a coil like this, okay, and then I have the current passing through the coil, coming here. I'll use the color blue to represent the current. So this might seem confusing, but anyways, coming down that face, going around the back, coming down the front, around the back, down the front, around the back, down the front, around the back, and out. So it's coming in like this and out like that. And what would happen is this would behave like a bar magnet, with this end being north and that end being south. Okay? Now, what does a magnetic field look like around a bar magnet? Well, it looks something like, oh gosh, it looks like these loops, if you remember. Okay, like this, something like that. And the arrows always point towards S. So my arrows would be pointing that way. Okay, coming out of the north side. Okay, and going into the south side. Okay, so they always point away from the north and towards the south. So that's what a magnetic field looks like around a coil. Now there is a right-hand rule for this. Okay, the right-hand rule goes like this. You take your right hand, your fingers this time indicate the direction of current. In this case, the current is going up the front face. Okay, so you see how his fingers are pointing in that direction. His fingers are pointing that way, right? And this time the thumb will point to the north pole of the solenoid, because the solenoid will now act like a bar magnet. In fact, we call this I'll use black again. This is an electromagnet. I actually have one at school I would have shown you. That, you know, I have very strong magnets, permanent magnets, that you can try to pull apart and it's really impossible. And then I also have a solenoid that is way, way stronger than those bar magnets. It's impossible to pull off something once it attaches, if it's like, you know, say a bar of iron or something. It's very, very strong, and it's powered by just a 9-volt battery. Okay. But anyway, an electromagnet. Electromagnet is when we use electricity to produce magnetism. Okay. All right. So anyway, that's basically it for how electricity can be used to create magnetism in straight wires and coils. Okay. But now, and this is very, very significant, the opposite is also true. Okay. Moving charges produce magnetic fields, while moving or changing magnetic fields produce electric fields which can induce electric current. This is called electromagnetic, I'm going to just say EM, induction. And when you think about this, when they discovered this, again, probably something else that was discovered by accident, but when they discovered this, this is probably one of the most significant discoveries of all time, because this is how we produce electricity on a large scale. Okay? So let me show you what I mean. We're going to use coils to demonstrate. So here I've got another one of these things. Let's see if I can make it work. Okay. That's going to give me the cookie warning again. All right, so look, here's the deal with this. Okay, here we go. Now you can see the whole thing. That's good. All right, so look, this, I have a bar magnet, and then I have a coil. Now the coil has no power supply, but it does have a load attached to it. You see the little resistor there. So here's the deal. If I take my bar magnet and I shove it towards the coil, then it'll induce a current in the coil. Okay. Now if I pull away my bar magnet, okay, it also induces a current. But if I stop moving it altogether, which I can't do here, it's just going to keep going. But if I stop moving it altogether, then the current stops too. Okay, you have to keep working to keep the current going. Now, this might seem like a kind of interesting little experiment, but this is how, like, the electricity that you're using right now to look at your phone or look at your laptop or whatever the case may be, that electricity comes from somewhere. Well, it comes from turbines, okay? And turbines are spinning systems that use this principle of electromagnetic induction so that the moving magnet or the moving coil, doesn't matter which one's moving, by the way. You could keep the magnet steady and move the coil. Whatever's moving, as long as they're moving relative to each other, you're going to get current. And this is how we produce electricity on large scales. So when they discovered this, it changed the world, right? Well, for better or for worse, changed the world. We were able to create electricity on scales that could power cities. Okay, before that, you're using a lantern to light your house, okay? Like with a fire inside, okay? Candle light, basically. And it was like that for, hundreds of years. Well, now all of a sudden, you produce electricity. Now, inventors come along, produce all these electric devices, including a light bulb. Wow, I'm tired. Okay, so look, here's the deal. Notice, if I push my magnet this way, okay, so this is my movement, that's the motion of the magnet. That is a magnet. that is a coil. Now, if the magnet is moving towards my coil, the coil will try to oppose that action. Right? So it'll try to repel it. I'm trying to push them together. It tries to repel. And when it does that, current gets induced in the coil. Now, if I use my right-hand rule, okay, and my thumb points towards the North Pole, then my thumb will point that way, okay, towards that North Pole. And then I'll find, if I wrap my fingers around, the current is traveling down the front face of this solenoid, okay, and then around the back, down here like these red arrows that they have here indicate, and that's it. Now, if on the other hand I reverse the direction of my magnet and now I pull it away, well, again, it tries to oppose, okay, the motion of the magnet. Now this is a little counterintuitive, okay? Like, so I forced them apart with my hand, okay? And it's gonna be a funny video, all these yawns. But anyway, I forced them apart with my hand, but the coil tries to pull it back. Now I'm always gonna win this because if I stop trying to force it, the coil won't induce any current. And so it just won't work at all. All right, so what'll happen is it could never beat me or pull harder than I'm pulling. It can only like resist. And so I'll feel a little resistance, but I will still win. And if I stop doing it, if I stop moving my magnet, it stops too. So the current will collapse in here. Now if I use my right hand rule, this time the North Pole is over there. Okay, so I point my thumb at that. My fingers now will point this way, up the front face. Okay, and we'll find that our current is following these red arrows, and the current has reversed compared to a diagram here. Call that one A, call this one B. Now if you look at the animation, you can see this happening. Okay, when the magnet is moving towards it, a North Pole gets induced to try to repel the magnet. But when you pull that North Pole away, a South Pole gets induced close to it, okay, right there, close to it, and it tries to pull it back. Okay, it'll never win, but it'll try. Okay, it'll always try to oppose you. And so we call this Lenz's law. Oops, with a Z. Okay, the induced current, which is in the coil, always opposes the inducing action. Okay, so what that means is it produces a magnetic field that tries to oppose the motion. Okay, and that's Lenz's law. All right, now, like I said, this is critical science. This, like, how many things have we talked about? You know, you can talk about Newton's laws and everything else, and yeah, they're very important, allow us to go to the moon, for example. But, you know, when you think about something that completely changes society itself, okay, this discovery of electromagnetism, that magnetism creates electricity, was massive, because before that we just had batteries. Okay, now we have turbines that can be, you just have to find a way to spin them, some kind of force to spin them, like the wind, like nuclear power, like those other power sources we talked about before. Okay, like thermal generation and etc. to turn the turbine, right? So if you need to turn a turbine, you just need to find an energy source to do that. And if you can just, as soon as you make it turn, I mean, you could ride your bicycle, you could turn the turn by hand. It'll produce electricity if you do that. Okay. All right. So here's the deal. I wanted to show you a couple of applications of this. All right. This first picture is an AC generator. It generates alternating current. Okay. Now you see the engineer looks at this and says, okay, if you keep that magnet moving, it'll produce electricity, okay, in the coil. But how do I make it so it's easier to sort of get the relative motion going? Well, maybe a spinning system, right? So here we see the basic design of turbines, where you have a spinning system. There's no power source in this circuit, okay? No power source at all. There is a load, that's the green resistor you see at the bottom. There's a magnet here, okay, a U-shaped magnet, and the blue lines going down indicate the magnetic field of that. Now these two rings here are called slip rings. There's brushes that brush against it so that the electricity can exit the coil, which is one loop of wire, and flow through the circuit, okay, into the meter, into the resistor. So if you look at this, it's kind of an ingenious design. You've got these rotating rings, and then these brushes here brush against the rings, carrying electricity in and out of the rings and into the circuit. Okay, so that's an AC generator. All right. Now I'm going to show you a DC generator. See if you can spot the difference. Okay, this is a DC generator. What you'll notice right away is now we have a light bulb here, and no meter this time, but really that doesn't matter. Okay, and if you take a look at this where it says north and south, so here's our bar shape, our U-shaped magnet, same, and a coil, same as the AC generator. Okay, very similar. But look at the ring. There's only one ring this time, and it's split in half. So we call this a split ring commutator. Here, these black cylinders touching them are the brushes. This one has brushes too. It has red brushes brushing against those two rings. But this only has one ring, but it's split in half. Okay, and the brushes brush against it as well. Okay, this is a DC generator. Generates DC current. All right, one more thing. Let's see if you can guess what this is. All right, this is a wind turbine. Okay, and so the blades get hit by wind, and it spins the turbine. And the turbine is this blue cylinder that you see inside the device, okay? And then what happens is that electricity that it produces because of the turning, okay, there's probably a gear mechanism in here too, which multiplies the spinning rate, okay, of the blue generator. But anyway, now this will produce electricity for us, okay? And I'm just going to write this down. It's very important. I'm just going to say, oh, here. First I'll say that this is a wind turbine. I'm just going to say note. EM induction. My computer is really laggy, just like myself right now.